Hey folks, Todd Coburn with your Aerospace Structures series. This video is on NASTRAN and it's on coordinate systems, how to define a coordinate system. We're going to cover three basic coordinate system cards: a rectangular, a spherical, and a cylindrical coordinate system card, so stay tuned. If you want more specific, detailed help, you'll want to get the NASTRAN primer. You can see a link to that, which teaches the most fundamental NASTRAN skills that every finite element analyst should understand. So first we're going to look at those basic cards. This is the form of the CORD 1R card, which is one of the ways to define a rectangular coordinate system. Now remember, when you make a NASTRAN model, you're going to be typically using the global coordinate system, which is a rectangular coordinate system, X, Y, Z, or 1, 2, 3. Okay. When you want a different coordinate system, like in order to restart the clock, or rectangular coordinate system that's identified with a different orientation, use the CORD 1R card as one of the ways to do that. Now, the way you specify that card, this little sketch will help. The first, so you've got the coordinate system, or the card ID, CORD 1R, the CORD 1R name of the card. You have the coordinate system ID, which you put here in field 2. So if a grid point calls out this coordinate system, then it will use it. So we're going to then have the grid points 1, 2, 3. The first grid point goes at the origin of this new coordinate system. In this particular case, let's say that point 1 is where you want it. You put the origin right there. Okay. The second one, not so intuitive. Usually we go for the X direction first. The second coordinate defines your Z-axis. So you have your first grid point, and as you'll see here, the Z-axis is going to be along the 2 direction. So wherever that second coordinate is, that will define what that is. Now your third coordinate, or grid point, grid 3A, that will define the X-axis, but the way it does it is you drop that point anywhere in the XZ plane. Then what will happen is NASTRAN will project that vector from 1 to 3 down onto your in that plane and project that down to your X-axis. So that's how it defines it. So 1 on the origin, 2 on the anywhere on the Z-axis, the positive Z-axis, and 3 anywhere in the XZ plane, and with the orientation of that being to the right or left of the Z-axis, that will define what the direction of the X-axis is. It'll be the projection of that perpendicular, dropping onto that plane that's perpendicular to that 1, 2 vector. Okay? So your basic procedure is to place your first node at the origin of that coordinate system. Not the origin of the global coordinate system, the origin of the coordinate system, the local coordinate system that you want to define. Your second node goes anywhere along the Z-axis, and there's an example. And the third one goes anywhere in that XZ plane. Now, being humans, a lot of times dropping a point in a plane, which we then have to project, is not so intuitive. So a clearer way to do this, the way I recommend, is this, where we drop the first node same way as before, the second node along the Z-axis same way as before, but then instead of placing that third node somewhere in this arbitrary plane, go ahead and drop it right on the X-axis. Whatever direction you want the X-axis to be, put that third node on the X-axis. There are cases where that's not convenient and you want to use the primary form of the card that's shown on the left, but very commonly this will be clearer and make it easier for you to not make mistakes. So that is how we define a rectangular coordinate system. Remember, our X-axis is from grid point 1 to along the X-axis, which is either projected or specifically defined based on the placement of your G3. The Y-axis is now perpendicular. It's in that plane perpendicular to the XZ plane, and your Z-axis is the 1, 2 vector defines that. Got it? So that's how you define a rectangular coordinate system. Now we're going to go and introduce the cylindrical and spherical coordinate systems, and then I'll show you some examples on how this card is used. Okay? This is the CORD 1R card. This is a cylindrical coordinate system. This is a great card to do, for example, if you're making a cylindrical structure, like a fuselage or a rocket. What you can do is define a cylindrical coordinate system and then strike off the points with that cylindrical coordinate system with the r, theta, z values. So the way this one works is quite similar, and we got the graphic from the NASTRAN manual here. Your first node goes at the origin. Your second node again goes in the z direction, and that will define the 1, 2 vector, defines the z axis. Your third node again gets placed anywhere in the xz plane. The projection of that down onto the perpendicular axis will define the x coordinate, and then the y will be perpendicular to that. Now I recommend, once again, drop that third node directly on the x-axis that you want, and then you're going to get your points will be defined in a cylindrical coordinate system, r, theta, z kind of system. Okay, and then the third card we want to look at is the this is whoops. Now this is how that card looks. This is the form of the card. Once again, you have the CORD 1R, that's the name. You have the coordinate system ID. You have the grid point 1, 2, and 3, where 1 is placed at the origin, 2 is placed on the z-axis, 3 is placed so that the projection of that will define the x-axis, and then you can actually define 2 coordinate systems on one line, which is what the fields 6 through 9 do, is give you a chance to identify another local coordinate, rectangular coordinate system. Now the cylindrical coordinate system card looks like this. We will use the graphic from the manual here once again. Now we're going to use a CORD 1C. What this is good for is if you're trying to strike off any cylindrical structure, such as a fuselage, where you might want to call out the r, theta, z position. You can do that with this card after defining the coordinate system. So you're going to have your coordinate system name, CORD 1C, the ID, which is like 1, 2, 3, 4, whatever, whichever the ID you want to give that coordinate system. Your grid point, your first grid point, once again, is going to go at the origin of that coordinate system. The second grid point will again define the z-axis, just like we saw before, and the third coordinate will again define the xz plane, the projection of which will define the x-axis. As before, I recommend drop that point, that third point, directly on that x-axis whenever possible, but you can also just drop it in the plane. Then what happens is your coordinate system has the x, y, z. It's going to define r. You put in your r, and then your theta, which is the angle rotating about the z-axis that point is, next point is going to be, and then the z position. So r, theta, z, and this is how you define it. Okay, got that? And there's some more information on the card. You can get this out of the NASTRAN manual or any NASTRAN handbook. Okay, the next one is the CORD 1S, which is a spherical coordinate system. This is the form of the card. Once again, you have the name of the card, the CORD 1S. You have the ID of that coordinate system. You have a G1, G2, T3. And once again, you can see you can put 2 different coordinate systems on the same card. The G1 is again at the origin. The G2 is again anywhere along the positive z-axis. Your G3, once again, can be dropped anywhere in the xz plane, and the projection of that onto the x-axis will define that x-axis. But once again, I recommend you drop that third node directly on the x-axis so it's crystal clear, and then you're going to have an r and a theta, a phi now, a theta and a phi, where theta is the angle made with the z-axis of your vector, and phi is the axis made with the x-axis, just like when you're dealing with direction cosines. Okay, got that? So those are three of the ways that we can identify a local rectangular cylindrical and spherical coordinate system. I'll show you how you actually activate using these in just a moment as we go through an example. So here is our grid card, a typical grid card. Now notice we covered the grid card before. Notice this CP in field 3. When you have a grid card, notice you've got grid, you've got the ID of the grid point. We usually leave this next third field blank. And what that does, it means that your coordinates, your 0, 0, 0 and your 10, 0, 0, will be defined in the global coordinate system. Okay, so that first field, that CP field, the C in the third field called CP, if you put a number there, an ID there of a coordinate system card, it will use that coordinate system. So if we had defined a coordinate system called 1, like a rectangular coordinate system, and if we put a 1 in that third field of grid point 1, now it'd be looking for, it would be defining that 0, 0, 0 would be in the local coordinate system. Let's say that we defined a cylindrical coordinate system, we called it 2, and if we had a 2 in that third entry of grid point 1's card, then that means that the 0, 0, 0 would be defined in that spherical coordinate system that was identified. You'll notice also here, over here in field 7, we have another coordinate system. And that coordinate system, whenever we put something there, now you'll notice in this case, in grid point 1 and 2, that there's nothing after the last, the XYZ value, nothing after the Z value, so it's not using that. But if we had put a comma and put some ID, then it would use that coordinate system. So if you put the ID of a local coordinate system, rectangular coordinate system, it would use that, not for defining the point, because it used that field 3 coordinate system for that. It uses it for how it gives the output. Now notice when we leave this blank, that means all output will be in the global coordinate system. You'll get translations, X, Y, Z in the global system. That means forces and displacements global. The 4, 5, 6, which are all moments, and displacements, rotations, 4, 5, 6 rotations are all in the global coordinate system. But if you had instead put in that 7th column of entry on that card, if you would put the ID of a cylindrical coordinate system, then what the NASTRAN will output is deflections and forces in the cylindrical coordinate system. That's pretty cool, and it's pretty powerful. Okay, so we'll take a look at how this plays out in an example in just a minute. So what we're drawing attention to is that while we've been using the grid point cards for a while, this field 3 where we can define a different coordinate system to define the location of the grid point, and grid 7 where we can use a different coordinate system to identify how we want those deflections and forces to be defined. If they're blank, you're using the global coordinate system. Okay, so that's how that works. All right, so this is some drawing attention to those fields and the CD, the CP, which is your definition, and the CD, which is your output. Okay, so let's take a look at an example. This is a little example from a homework problem I give my students. Notice we have 3 pins. This pin 1 is actually the origin of the global system, X to the right going toward 2 and Y going up toward going toward 3. We have 3 rods. We have a force. There's a roller here and a roller here. Now, while these are 3 pins, the problem is using the global system, you will not be able to define this roller using a global system. What you have to do is make a local system so that you can enforce a constraint in that perpendicular to the support direction and allow it to roll and deflect along that inclined surface. And so we can actually do this with just a simple rectangular coordinate system, and that's what we're going to do here. Okay, we're going to actually add a couple nodes. So let's take a look at the full deck. Once again, we're going to use this Chord 1R card. We put our first node at the origin. Now the origin of the global system is here at 1. And this is where we want to introduce this new localized system so we can put it at the same place. So 1, we put our first node at 1 at 0, 0, 0, and that defines the origin of our new coordinate system. We're going to put the second one along the z-axis. Now, since we have x to the right and z and y going up, that means coming out of the page. So anything at the anything, any number will do that. And so you'll see down here, we can add a grid. This is adding grid 10, 0, 0, 30, puts that Z point 30 inches away from the page. And then we need to drop our third node on the x-axis. Now this is a 45-degree angle, so all we have to do is drop a point over 1 and down 1, or any scalar magnitude of that. So you'll notice grid 40, which is just an arbitrary number, is defined in the global coordinate system also, and it's located 1 inch to the right of 1 and 1 inch down. What that does is define the x-axis right down along that 45-degree surface. We're going to go ahead and fix those 2 additional nodes because we don't have anything attached to them. Therefore, they'll cause a singularity with our run. So we just fix those points. Those are just in the model to help define that coordinate system x, y, and z. Okay, and down here is the chord system. You'll notice we have chord 1R, we have ID 1, ID 10, ID 40. 1 defines the origin, 10 is along the z-axis, 40 defines a point along the axis. Everything else is the same. So actually we can write out, this is our model, the bulk data file. Notice we have our 3 nodes, which are our basic model defined in global system. See, all these are blank in here. So those are all defined with a global system. Here, 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 then 30 inches out of the page, and then 1 over and 1 down. That is our model. The nodes 10, 1, 10, and 30 are the 1, 10, and 40 are the ones that we're going to use to define that coordinate system, which you see down here in the chord 1R card, where it goes from 1 to 10 to 40. And notice also that at that node 1, we've defined this coordinate system for a reason, so we can define sliding. But if you don't do anything else but make this coordinate system, your output will be the same, and you still will get global output at node 1. What we want to see is output in this new coordinate system, this new rectangular coordinate system that we identified is coordinate system 1. And to do that, we put here in the 7th field, 1, 2, 3, 4, 5, 6, 7th field, we put the ID of that coordinate system. Now look, we're identifying that point in the global system, but we want any output and deflections in that local coordinate 1 system. Now the output will show, if we show a x deflection at node 1, it will actually mean positive down along the incline. A negative x deflection will be upwards along the incline. A positive force in the y will mean we have a reaction pushing up perpendicular to that surface. And a positive in the x would be wrong, means something's wrong, because that roller means you're not going to transfer any forces. So that's how it works. Notice we use the coordinate system to find that inclined surface. Then we called out our displacements and reactions at node 1 in that new coordinate system. And everything works great. So go ahead and practice that on little simple models till you're confident that you understand it, and then you can go and start implementing in your larger models. Enjoy.